Hello there, and welcome to the Sleeping Physicist. If you're someone who likes to unwind by thinking about stars, particles, and the quiet structure beneath the universe, you're in the right place. Tonight, we'll let our attention drift gently into real physics and real discoveries. Some of what you'll hear may sound unfamiliar at first, but all of it is grounded in careful observation and well-tested theory. And if you enjoy these slow explorations, you're always welcome to like and subscribe. But for now, get comfortable, let your body rest, let your thoughts wander, and settle in with me. What is nuclear energy made of, according to quantum physics? When we talk about nuclear energy, we usually begin with its effects rather than its substance. We see water boiling inside a reactor, turbines turning, lights glowing in distant cities. We see the steady warmth of the sun reaching Earth after a long journey through space. In more extreme moments, we've seen sudden flashes of light and heat released from very small amounts of matter. These are not subtle effects. They are measurable, repeatable, and unmistakably real. Something inside matter is capable of releasing enormous energy, far beyond anything chemical reactions can provide. If you imagine holding a small pellet of nuclear fuel in your hand, nothing about its appearance hints at this power. It doesn't feel hot, it doesn't vibrate, it doesn't glow, and yet, under the right conditions, that same material can release more energy than tons of coal or oil. This contrast is one of the first clues. Nuclear energy is not about motion we can see or heat that is already present. It is about something stored, quietly, in the structure of matter itself. To make sense of this, it helps to think about energy not as a substance flowing like a fluid, but as a capacity for change. When nuclear energy is released, what we observe is motion, heat, radiation, and light appearing where they were not before, which means that before the release, that capacity must have been held in a different form, not in chemical bonds between atoms and not in mechanical tension, but somewhere deeper and far more compact. This is why early experiments with nuclear reactions were so startling to physicists. The energy did not come from rearranging atoms into new molecules. It came from transformations within atoms themselves. And because those transformations happened at incredibly small scales, the energy involved was concentrated to an extraordinary degree. Once this was measured and confirmed, it became unavoidable to conclude that nuclear energy is tied directly to the internal structure of matter, not to its surface behavior. This realization leads naturally to the next step. If nuclear energy comes from inside atoms, then understanding what it is made of means understanding what atoms are made of and which part of them is responsible for holding such vast reserves of energy in silence. The moment we look closer, the atom stops being a tiny solid object and becomes a layered system. Most of its volume is empty space, with lightweight electrons moving in delicate patterns far from the center. These electrons are responsible for chemistry, for flames, for batteries, for nearly every energy source we encounter in daily life. When chemical energy is released, it is always these outer regions of atoms being rearranged, trading partners, settling into slightly lower energy configurations. But nuclear energy does not respond to chemistry at all. Heating, cooling, pressure, or mixing substances barely affects it. This tells us immediately that the source must lie deeper than the electron cloud, in a region untouched by chemical change. At the very center of the atom sits the nucleus, unimaginably small compared to the atom as a whole, yet containing almost all of its mass. If the atom were the size of a cathedral, the nucleus would be a grain of dust suspended at its center. What makes this important is not just size, but density. The nucleus packs protons and neutrons into a volume so compact that ordinary intuitions about matter begin to fail. The forces operating here are not gentle. They are intense, short-ranged, and deeply quantum in nature. And because the nucleus contains nearly all the atom's mass, any change to its internal structure has consequences far larger than changes involving electrons. Early nuclear experiments made this unmistakably clear. When nuclei changed, either by splitting or combining, the energy released dwarfed anything seen in chemistry. This was not because nuclei were doing more work in the usual sense, but because something fundamental about their internal makeup was being altered. The atom was no longer acting like a container for reactions. It was revealing itself as a reservoir. This realization quietly reshaped physics. Energy was no longer something that merely flowed between objects. It could be locked into matter itself, concentrated at the core of atoms, waiting for the rare circumstances where the nucleus is persuaded to rearrange. To understand what that rearrangement involves, we have to look directly at the nucleus and how its constituents manage to stay bound together at all. Inside that tiny central region of the atom, protons and neutrons are pressed together so closely that their individual identities almost blur. These particles, known collectively as nucleons, are not arranged with space to spare. They are confined within a region only a few trillionths of a millimeter across, held in a balance that is both stable and tense. This extreme confinement is the first key to why nuclear energy exists at all. Protons carry positive electric charge, which means they naturally repel one another. If electric forces were the only ones at work, the nucleus would immediately fly apart. The fact that it does not tell us something powerful is counteracting that repulsion. Neutrons, though electrically neutral, play a crucial role in this balance, helping hold the nucleus together without adding additional electrical push. Even so, electrical repulsion never disappears. It is always present, always straining outward. What keeps the nucleus intact is a different interaction entirely, one that only becomes significant at very short distances. This force does not reach far. It does not influence atoms from across a room or even across an atom. But within the nucleus, it is overwhelming. It binds nucleons together with an intensity far greater than electromagnetism can provide at that scale. And because this binding happens in such a small volume, the energy involved is immense. You can think of the nucleus as a system under constant internal pressure. Forces pulling apart and forces holding together are locked in a precise, delicate competition. The nucleus is not relaxed. It is stable, but only just. And that stability depends on the exact arrangement and number of protons and neutrons inside. Change that arrangement even slightly, and the balance shifts. This is why nuclear transformations are so consequential. When a nucleus changes its structure, it is not merely adjusting its shape. It is rebalancing forces that are among the strongest in nature, confined to one of the smallest regions that exists. The energy released or absorbed in that process reflects how tightly or how loosely those nucleons are bound together. And to understand that binding, we need to look at how mass itself participates in storing energy inside the nucleus. When physicists began carefully measuring nuclei, they noticed something subtle and unsettling. If you add up the masses of the individual protons and neutrons inside a nucleus, the total is always slightly larger than the mass of the nucleus itself. Nothing appears to be missing in any ordinary sense. No particles have escaped. And yet, the combined object weighs less than its parts. This difference is small, but it is real, repeatable, and measurable. It is known as a mass defect, and it is one of the clearest windows into what nuclear energy is made of. The missing mass has not vanished. It has been converted into energy, stored in the nucleus as part of what holds it together. The nucleus is lighter precisely because energy has been invested to bind it. This is where a profound idea quietly enters physics. Mass and energy are not separate categories. They are different expressions of the same physical quantity. When nucleons bind together, some of their mass becomes binding energy, locking the nucleus into its specific structure. That energy does not move, it does not radiate, it simply exists as part of the nucleus's identity. An analogy can help here, used carefully and only once. Imagine compressing a spring and locking it in place. The compressed spring weighs slightly more than a relaxed one because energy has been added to the system. In a nucleus, the situation is reversed. Energy is released when nucleons bind, and the bound system weighs less. The energy that could be released later has already been accounted for in the nucleus's reduced mass. This is why nuclear reactions are so powerful. When a nucleus changes in a way that alters how tightly its nucleons are bound, the difference appears as released energy. Heat, motion, and radiation are not created from nothing. They are the visible forms of mass that was quietly present all along, converted as the nucleus rearranges itself. Once this is understood, nuclear energy stops being mysterious. It is not hidden fire or exotic fuel. It is the stored energy of mass itself, shaped by how particles bind together at the smallest scales. And the amount of energy stored depends entirely on how stable that binding is, which brings us to the idea of nuclear stability and why some nuclei hold more energy than others. Not all nuclei store energy in the same way or to the same degree, holding together but only temporarily. This difference comes down to binding energy, which is the amount of energy required to pull a nucleus completely apart into separate protons and neutrons. A nucleus with high binding energy per particle is deeply stable. Its components are held together so efficiently that there is little advantage energetically in changing its structure. Other nuclei are less tightly bound. They exist in configurations where a different arrangement would lower the total energy of the system. When such a change becomes possible, energy is released as the nucleus moves toward a more stable state. You can picture this without imagining motion or heat at first. Think instead of a landscape with hills and valleys. A stable nucleus sits in a deep valley. An unstable or less stable nucleus rests higher up, not falling because a path is missing, but always able to release energy if a route downward appears. Nuclear reactions provide that route, allowing the nucleus to shift toward a configuration with greater binding energy per nucleon. What matters here is that energy release does not come from destruction, but from improvement. The nucleus releases energy because it becomes more stable than it was before. That energy difference emerges as motion of particles, as radiation, as heat, but at its origin, it is simply the consequence of the nucleus settling into a lower energy arrangement. This also explains why both splitting heavy nuclei and fusing light ones can release energy. Very heavy nuclei are often less tightly bound per particle than medium-sized ones. Very light nuclei can increase their binding by joining together. In both cases, the direction is the same. The system moves toward greater nuclear stability, and the excess energy appears in the world we can measure. Binding energy, then, is the quiet ledger behind nuclear power. It keeps track of how much energy is stored in the arrangement of nucleons, and how much can be released when that arrangement changes. And the force responsible for creating this binding in the first place is unlike anything else we encounter in everyday physics. The force that makes binding energy possible is called the strong nuclear force, and it behaves unlike anything we experience at human scales. It does not reach across rooms or planets. It does not fade gently with distance. Instead, it switches on powerfully only when particles are extremely close, closer than the size of a proton itself. Within that tiny range, it overwhelms every other interaction. This force is what allows protons to remain pressed together despite their electrical repulsion. At nuclear distances, the strong force is so intense that it effectively glues nucleons into a single object. But it comes with a strange limitation. Move those same particles just slightly farther apart, and the force drops away rapidly, offering no long-range pull to keep the nucleus intact. An analogy can help, briefly and carefully. Imagine Velcro that only works when two surfaces are already pressed firmly together. When they touch, the grip is powerful, but at even a small separation, there is no attraction at all. The strong force behaves in much the same way. It does not gently draw particles inward, it binds them only once they are already close enough. Because of this behavior, nuclei exist in a state of compact tension. They are not held together by a gradual pull, but by a short-range lock that requires particles to remain packed tightly. This is why nuclear matter is so dense, and why changes to nuclear structure involve such dramatic energy shifts. Breaking or forming these bindings means working directly against one of the strongest forces known in nature. The strong force also explains why nuclear reactions are rare and difficult to initiate. Particles must be brought extremely close together before anything can happen. Once they are, the energy landscape changes suddenly and decisively. And beneath this force, beneath even protons and neutrons themselves, quantum physics reveals an even deeper layer to what nuclear energy is truly made of. When quantum physics looks inside the nucleus, It finds that protons and neutrons are not solid building blocks in the usual sense. They are not tiny marbles pressed together. Instead, they are dynamic patterns formed by deeper quantum fields, constantly fluctuating even while the nucleus appears stable from the outside. What we call a particle here is really a persistent vibration, held in place by the rules of quantum interaction. Inside each proton and neutron, smaller constituents interact through fields that never fully rest. Energy is not localized at a point. It is distributed through these fields, shaping how nucleons respond to one another. This means the strong nuclear force is not a simple pull or glue, but an emergent effect of underlying quantum behavior. The nucleus holds together because these fields arrange themselves into configurations that minimize energy under extreme confinement. This matters because it reframes what nuclear energy actually is. The energy stored in a nucleus is not sitting between particles like fuel between logs. It exists in the structure of quantum fields themselves, in how they are constrained, compressed, and balanced against one another. When a nuclear reaction occurs, those fields are forced into a new arrangement. And because the rules of quantum physics demand precise energy accounting, the difference between the old arrangement and the new one must appear as released energy. In this view, nuclear energy is not released from matter so much as matter changes its internal rhythm. The fields reorganize. Some configurations require less energy to exist than others. When the nucleus transitions from a higher energy pattern to a lower energy one, the excess energy becomes motion, radiation, and heat in the surrounding world. This is why nuclear reactions are both subtle and profound. At their heart, they are quantum events. Tiny shifts in field configurations inside the nucleus ripple outward, producing effects large enough to power cities or stars. And depending on how nuclei are persuaded to change, this release can happen through two very different physical processes, each revealing a different side of nuclear energy. When a very heavy nucleus changes, it often does so by splitting. This process, known as fission, begins when a nucleus like uranium absorbs a neutron and becomes slightly unstable. That added particle does not explode anything by itself. Instead, it nudges the nucleus into a configuration where its internal balance can no longer be maintained. As the nucleus stretches and divides, the strong nuclear force begins to lose its grip. Remember how that force only works at extremely short distances. As parts of the nucleus move even slightly apart, the binding that once held everything together weakens rapidly. At the same time, the electrical repulsion between protons becomes more effective, pushing the separating fragments away from each other. The key point is that the two smaller nuclei formed by fission are more stable, per particle, than the original heavy nucleus. They have higher binding energy per nucleon. This means the total energy stored in their structure is lower than before. The difference has to go somewhere. It appears almost instantly as kinetic energy, with the fragments flying apart at tremendous speed and as radiation released by excited particles settling into new quantum states. What we observe outside the nucleus is heat. The fast-moving fragments collide with surrounding atoms, transferring their energy through countless tiny impacts. But the source of that heat is not friction in the usual sense. It is the direct conversion of nuclear binding energy into motion, triggered by a quantum rearrangement deep inside matter. Fission is therefore not a violent tearing apart, but a release of imbalance. The nucleus breaks because doing so allows its internal quantum fields to settle into a more energetically favorable pattern. And because the scale is so small and the force is so strong, the energy released is enormous. This same principle appears again in a very different form when light nuclei combine rather than split. When nuclei are very light, the path to greater stability runs in the opposite direction. Instead of splitting apart, these nuclei can release energy by coming together. Fusion begins when two light nuclei, such as forms of hydrogen, approach one another closely enough for the strong nuclear force to take effect. This is not easy. Their positive charges repel, and immense pressure and temperature are required to push them into the narrow range where nuclear binding becomes possible. Once that threshold is crossed, the change is sudden. The strong nuclear force takes over, binding the two nuclei into a single, more stable one. The resulting nucleus has a higher binding energy per particle than the originals. Just as in fission, this means the final configuration requires less total energy to exist. The difference is released immediately. In the heart of a star, this process happens constantly. The released energy appears first as the motion of newly formed particles and high-energy radiation. That energy then works its way outward, collision by collision, until it becomes the light and warmth that travel across space. The star shines not because it is burning, but because matter at its core is rearranging itself into more stable nuclear forms. Fusion shows the same underlying principle as fission, expressed differently. Energy is released not because something is consumed, but because the nucleus improves its internal balance. The quantum fields settle into a configuration that requires less energy to maintain, and once again, the excess appears as heat, light, and motion in the larger world. Whether nuclei split or fuse, the source of nuclear energy is the same. It is the difference between how much energy a particular nuclear arrangement requires and how much energy a more stable one needs. And this leads to the deepest answer of all. Nuclear energy is not a special substance hidden inside matter. It is the consequence of how matter itself is allowed to exist under the rules of quantum physics. At the deepest level, nuclear energy is not a thing stored inside matter. It is a difference. It arises because quantum physics allows matter to exist in multiple possible internal arrangements, each with its own energetic cost. A nucleus is one such arrangement, defined not by rigid parts, but by allowed quantum states shaped by forces, confinement, and probability. When a nucleus exists in a less favorable arrangement, it is not unstable in a dramatic sense. It simply occupies a state that requires more energy to sustain. Quantum physics does not forbid this, it only keeps careful track. And when a pathway opens that allows the nucleus to shift into a configuration that requires less energy, the accounting must balance. The excess energy cannot remain hidden, it must emerge. This is why nuclear energy is so unlike combustion or mechanical work. Nothing is being consumed, no fuel is burning. Instead, matter is transitioning between quantum possibilities. The released energy is the physical signature of that transition. It is the universe enforcing consistency, ensuring that energy before and after the change remains conserved. Seen this way, nuclear reactions are not violent intrusions into matter, but natural relaxations. They are matter, finding a better fit within the rules imposed by quantum fields and fundamental forces. The dramatic scale of the energy release comes not from aggression, but from efficiency. At nuclear distances, even small changes in configuration correspond to enormous energy differences. This understanding dissolves the idea that nuclear energy is mysterious or exotic. It is ordinary matter obeying extraordinary rules at very small scales, and because those scales are so compact, the energy involved becomes astonishingly dense. That density is the next piece of the puzzle, and it explains why nuclear energy stands apart from all other known sources. The reason nuclear energy feels almost unreal in its intensity is not because it is rare, but because of how tightly it is packed. The forces involved operate over distances that are unimaginably small, far smaller than atoms, far smaller than anything chemistry can reach. When energy differences exist at those scales, they are compressed into volumes so tiny that releasing even a fraction of them produces enormous effects. In chemical reactions, energy comes from electrons shifting their relationships, moving between atoms that are already separated by relatively large distances. The forces involved are gentle by comparison, spread out across space. In their nucleus, everything happens within a region where particles are nearly touching, where the strongest known force is active, and where mass itself is part of the energy balance. That combination makes each rearrangement extraordinarily potent. Another way to see this is to notice how little matter is required. A small amount of nuclear fuel can operate for years, not because it contains a special substance, but because its internal structure allows access to energy that is normally locked away. Most matter never changes its nuclear arrangement. It carries its binding energy silently from the moment it forms. nuclear reactions simply unlock a different configuration and let the difference escape. This density is not accidental. It is a direct consequence of how quantum fields behave under extreme confinement. When space is limited and forces are strong, the energetic stakes rise. Small structural changes have large consequences. Nuclear energy is dense because the nucleus is dense, and the rules governing it are uncompromising. Understanding this removes the last sense of mystery. Nuclear energy is not dangerous because it is unnatural. It is powerful because it reveals how much energy ordinary matter has always contained, hidden behind the stability of quantum rules. And that realization points gently outward toward a broader truth about matter itself. When everything is put together, nuclear energy reveals something quietly profound about matter. The solid world around us feels inert and settled, yet at its core, it is anything but empty or passive. Every atom carries a nucleus shaped by intense forces and precise quantum rules, holding energy not as fuel, but as structure. Matter is not just something that occupies space, it is something that actively maintains an internal balance. This means that the energy we release in nuclear reactions was never added later. It has been present since those nuclei were formed, forged in stars or violent cosmic events long before Earth existed. Nuclear energy is ancient. It is the residual imprint of how matter assembled itself under extreme conditions, preserved faithfully ever since. What makes this insight calming rather than unsettling is its consistency. Nothing about nuclear energy violates the everyday rules of the universe. It follows the same principle seen everywhere else. Systems move towards stability. Energy differences resolve. Quantum rules are obeyed without exception. The only difference is scale. When those rules act over nuclear distances, the consequences become dramatic. Seen this way, nuclear energy is not a special category of power. It is a reminder of how much is already contained within ordinary matter and how patiently it waits. Most of the time, that energy remains locked away, contributing silently to the mass and stability of the world. Only under rare and carefully arranged conditions does it reveal itself. And so, according to quantum physics, nuclear energy is made of the same thing as everything else in the universe. It is made of relationships, forces, and allowed arrangements. It is made of matter finding its place within the deepest rules of nature, and occasionally letting the difference be seen. Once this perspective settles in, nuclear energy begins to feel less like a dramatic exception and more like a quiet explanation for why matter lasts at all. The same binding that allows energy to be released under rare conditions is what keeps nuclei stable for billions of years. Without that deep reservoir of binding energy, atoms would not endure. Matter would not persist long enough for stars, planets, or life to form. Every stable nucleus represents a long-term truce between opposing forces. Electrical repulsion pushes protons apart. Quantum binding pulls them together. The outcome is not a compromise, but a precise balance where energy is minimized and structure is preserved. Nuclear energy is simply the record of how much effort it took for matter to arrive at that balance in the first place. This also explains why most matter never releases its nuclear energy. Stability is not fragile, it is resilient. Nuclei remain as they are because changing them requires very specific circumstances. Extreme temperatures, high pressures, or carefully arranged interactions are needed to disturb that balance. In everyday life, those conditions are absent, and so the energy remains locked away, contributing only to mass and solidity. From this angle, nuclear energy is not something matter wants to release. It is something matter has already spent in order to exist. The energy we sometimes recover is a partial refund, paid out when matter is persuaded to reorganize itself into a more stable form, and that reorganization is governed, always, by the same quiet quantum rules that shaped the universe from its earliest moments. This continuity is the deeper comfort in the idea. Nuclear energy is not a foreign force hiding inside matter. It is a consequence of matter being exactly what it is, everywhere and always, held together by relationships that favor stability, persistence, and order over chaos. At this point, it becomes helpful to let go of the idea that energy is always something moving or glowing. In nuclear physics, energy often appears as constraint. It exists as limitation, as tension, as the cost of holding a system in a particular form. The nucleus is not energetic because things are flying around inside it, but because quantum rules tightly restrict how its internal fields are allowed to arrange themselves. Those restrictions matter. Quantum fields prefer certain configurations and resist others. When a nucleus exists in a configuration that is allowed but not optimal, energy is effectively being stored in that resistance. The nucleus is stable, but it is stable at a higher energetic price than necessary. Nuclear energy is the difference between what the rules allow and what they prefer. This reframing helps explain why nuclear energy can be released so suddenly. When a constraint is removed or relaxed, the system does not trickle downward gradually. It transitions decisively into a lower energy configuration. The release feels abrupt because the underlying change is categorical. One set of allowed quantum states gives way to another. In this sense, nuclear energy is not waiting to escape, it is waiting to be unnecessary. Once a nucleus finds a way to exist with fewer constraints, the excess energy has no further role to play. It appears as radiation and motion simply because those are the remaining channels available. And this idea scales naturally. The universe, at every level, is shaped by what is allowed and what is forbidden. Nuclear energy is one of the clearest demonstrations that energy is often the price paid for structure itself. Once energy is understood as constraint rather than motion, something unexpected becomes clear. Nuclear energy is not loud or restless at its source. It is remarkably still. Inside a stable nucleus, nothing is trying to explode. Nothing is rushing outward. The quantum fields that define protons and neutrons exist in patterns that have already settled into long-term balance. What makes nuclear energy powerful is not activity, but restraint. This stillness is easy to miss because we usually encounter nuclear energy only after it has been released. We see heat, radiation, spinning turbines, brilliant light. But all of that motion exists only after the nucleus has changed. Before that change, the energy is not circulating. It is not flowing. It is simply embedded in the rules that say this configuration must cost this much energy to exist. Inside the nucleus, quantum uncertainty does not mean chaos. It means precision without rigidity. The positions and momenta of particles are not fixed, but the overall structure is sharply defined. The nucleus occupies a narrow set of allowed states, fenced in by powerful forces and strict quantum conditions. That confinement is where the energy resides. A useful way to feel this intuitively is to imagine silence under pressure. Consider a deep ocean trench, where water is not rushing or turbulent, yet pressure is immense. The stillness does not imply absence of force. It implies balance. Nuclear energy is like that. The pressure is real, the forces are enormous, but they cancel so precisely that nothing moves. This explains why nuclear energy can exist for eons without changing. A uranium nucleus can remain intact for billions of years. A helium nucleus formed in the early universe can persist almost indefinitely. The energy bound into their structure does not leak away because there is no permitted pathway for it to do so. Quantum physics is not permissive. It allows only specific transitions under specific conditions. When those conditions are finally met, the change feels dramatic precisely because it has been delayed so long. The nucleus does not gradually unwind. It shifts state, and when it does, the energy that had been bound into stillness becomes visible all at once. Motion appears where there was none. Radiation emerges from silence. This also reframes the emotional response many people have to nuclear energy. It is often associated with danger or volatility, but at its foundation it is neither unstable nor aggressive. It is disciplined. It follows rules more strictly than almost any other physical system we know. The danger arises not from unpredictability, but from precision. When the rules allow release, they allow it completely. At a deeper level, this tells us something about the universe itself. Reality is not built from constant motion, but from allowed arrangements. Stability is not the absence of energy, but the presence of well-satisfied constraints. Matter exists because these constraints hold. Energy is stored because they do. Nuclear energy, then, is a reminder that the most powerful features of the universe are often the quietest. The forces that shape galaxies and stars announce themselves with light and motion. The forces that shape matter itself work in silence, beneath notice, defining what can exist and how long it may last. As understanding settles here, the question of what nuclear energy is made of feels less abstract. It is made of the cost of being matter at all. It is made of the energy required to hold structure together under the strictest rules nature has. And most of the time, that energy does exactly what the universe seems to prefer. It stays where it is, maintaining form, supporting persistence, allowing the world to remain exactly as it is, moment after moment, without needing to move. Once the stillness inside nuclear energy is understood, the next realization arrives naturally. The same quiet structure that holds energy inside a single nucleus is what powers the largest luminous objects in the universe. Stars are not exceptions to nuclear physics. They are its most patient expression. At the core of a star, conditions slowly and steadily overcome the barriers that usually keep nuclei apart. Gravity supplies pressure, squeezing matter inward for millions of years without haste. Temperature rises not as a spark, but as an accumulation. Eventually, nuclei move close enough for quantum rules to change what is allowed. Fusion becomes possible, not through violence, but through persistence. What happens next is subtle. Individual fusion events release energy in tiny amounts, at scales far smaller than the atom itself. No single reaction powers a star. What matters is repetition. Over time, countless nuclei shift into more stable configurations. Each shift releases a small difference in energy. Together, these differences add up to light, bright enough to cross galaxies. The star does not burn fuel in the way a fire does. There is no chain of destruction. There is only matter, slowly adjusting itself toward greater nuclear stability, one allowed transition at a time. The energy released supports the star against its own gravity, creating a long-lived balance. Gravity pushes inward, nuclear energy pushes outward. Neither wins quickly. This balance can last for billions of years. During that time, the energy released in the core travels outward in stages, interacting again and again with surrounding matter. By the time it reaches the surface, it has softened into warmth and visible light. What arrives at distant planets feels gentle, but its origin lies in the same constrained quantum stillness found inside every nucleus. Seen this way, nuclear energy is not merely a technological resource or a potential hazard. It is the mechanism by which the universe remains visible. Without nuclear binding and its gradual rearrangement, stars could not shine. Without shining stars, there would be no long-term sources of warmth, no stable climates, no slow chemistry unfolding on planetary surfaces. Even heavier elements owe their existence to this process. As stars evolve, they build increasingly complex nuclei, stacking layers of nuclear stability like geological strata. When conditions change, some stars release those elements back into space, not because nuclear energy demands release, but because gravity and structure reach new limits. Matter is redistributed, carrying its bound energy forward into new contexts. What remains consistent throughout all of this is the character of nuclear energy itself. It is never impulsive. It never acts without conditions. It responds only when the rules permit, and when they do, it responds fully. The same physics governs a single fusion event in a laboratory and the life cycle of a star. This continuity brings the idea of nuclear energy back down to Earth. The energy used in reactors, the energy that once shaped stellar cores, and the energy locked inside the atoms of your own body, all arise from the same source. They differ only in circumstance, not in nature. At every scale, nuclear energy reflects the universe's preference for stable arrangements. Matter forms, forces balance, quantum rules constrain what is possible. Energy appears as the cost of maintaining those constraints and as the reward for improving them. Nothing more is required. And so, nuclear energy is not something added to the universe later. It is not a feature layered on top of matter. It is present wherever matter exists, embedded in the very act of being held together. Stars merely reveal it continuously. Reactors reveal it deliberately. Most matter reveals it never at all. The universe does not rush this process. It allows energy to remain bound for unimaginable lengths of time. It allows matter to persist. It allows structure to endure. And when energy is finally released, It does so not as chaos, but as a precise consequence of the same quiet rules that have always been in place. If there is a calm hidden inside nuclear energy, it is this: nothing is wasted, nothing is hurried. The deepest power in nature emerges not from motion, but from balance patiently maintained until change becomes inevitable. There is another quiet dimension to nuclear energy that only becomes visible when we think in terms of time. Nuclear energy is not just dense in space, it is dense in duration. The energy bound inside a nucleus is often held there for timescales that dwarf anything familiar, spanning millions, billions, even trillions of years. Matter does not merely store energy, it remembers it. Every stable nucleus carries with it a history of formation. The binding energy inside it reflects conditions that may no longer exist anywhere nearby. Temperatures higher than any star now burning, pressures greater than those found in planetary cores, violent cosmic events that briefly allowed matter to rearrange itself into new nuclear forms. Once formed, those nuclei persist, carrying the energetic imprint of those ancient environments forward through time. This is why radioactive decay feels so strange when first encountered. Some nuclei change quickly, others wait for epochs. There is no visible countdown, no gradual warming, no outward sign that change is approaching. The nucleus simply exists in a quantum state that allows a transition but does not demand it. The energy remains bound until, without warning, the rules permit release. This behavior only makes sense in quantum terms. At the nuclear scale, time is not a smooth river. It is a set of allowed events separated by long stretches of stillness. A nucleus can exist unchanged for billions of years and then alter its state in a fraction of a second. The energy released does not build up toward that moment. It has always been there. In this way, nuclear energy acts like a time capsule. It preserves conditions from the deep past and delivers them into the present when a transition finally occurs. When we measure radioactive heat inside Earth, we are feeling energy released by nuclei formed long before the planet itself existed. When a reactor operates, it draws on energy bound into matter during stellar processes that ended before the solar system formed. This temporal aspect helps explain why nuclear energy can feel disproportionate. It is not merely concentrated in space, it is accumulated across cosmic time. Energy that could not be released under ordinary conditions has been waiting, unchanged, until circumstances allow it. When release happens, it compresses immense durations into a single moment of effect. What remains striking is how orderly this process is. Even across such vast timescales, nothing leaks, nothing erodes. The energy remains accounted for with extraordinary precision. Quantum rules enforce this discipline relentlessly. A nucleus either has an allowed pathway to change, or it does not. Time alone does not force the issue. This gives nuclear energy a strange neutrality. It is neither eager nor reluctant. It does not age. It does not decay in the usual sense. It simply persists until the universe presents a permissible alternative. In that sense, nuclear energy is patient beyond anything else we know. That patience is what allows matter to form complex structures. If nuclear energy leaked easily, atoms would not remain intact. Planets would not retain heat in steady ways. Stars would burn out almost instantly. The universe would be loud, brief, and hostile. Instead, energy remains locked into matter, released only in measured, rule-governed ways. From this perspective, nuclear energy feels less like a resource and more like an archive. It is the universe's way of preserving energetic information across immense spans of time. Each nucleus is a record of how matter once arranged itself, and a promise of how it might rearrange again, given the right conditions. And this brings the question full circle. What is nuclear energy made of, according to quantum physics? It is made of relationships frozen into matter. It is made of forces balanced so precisely that change becomes rare. It is made of energy constrained by rules so strict that time itself becomes almost irrelevant. When nuclear energy is finally released, what we witness is not the sudden creation of power, but the unfolding of a long-held possibility. matter shifts, fields reorganize, energy that has been part of the universe since its earliest chapters briefly becomes visible again. Most of the time, that energy remains silent. It supports the mass of atoms, it stabilizes the world, it allows the universe to be old, and in that quiet persistence, nuclear energy reveals one of the deepest patterns in nature. The universe prefers patience. It stores more than it spends. It builds structures that last, and only rarely allows them to change. And when they do, the change carries the weight of time itself. One of the quiet consequences of everything we have followed so far is an answer to a question that often goes unasked. If nuclear energy is so vast, if every nucleus contains such enormous stored energy, why does matter not simply come undone? Why does the world remain solid, predictable, and stable instead of constantly releasing what it contains? The answer lies in how strictly quantum physics governs permission. Energy alone is never enough to cause change. What matters is whether a change is allowed. A nucleus may contain an enormous amount of binding energy, but without a permitted pathway to a lower energy configuration, nothing happens. The energy remains locked in place, not by walls or barriers, but by rules. These rules are not negotiable. They are not statistical tendencies that eventually wear down. They are exact constraints on how quantum states may transform. A nucleus can only change if there exists a final state that conserves energy, momentum, charge, and all other required quantities simultaneously. If no such state exists, time itself becomes irrelevant. The nucleus will wait indefinitely. This is why ordinary matter is so dependable. The atoms in a table do not decay into radiation. The atoms in your body do not spontaneously release nuclear energy. The configurations they occupy are allowed, stable, and isolated from lower energy alternatives. Even though a more stable arrangement might exist in principle, the pathway is forbidden, and in quantum physics, forbidden means impossible. This perspective reframes stability as an active achievement rather than a passive condition. Matter is stable not because nothing is happening inside it, but because everything that could happen is disallowed. The nucleus remains intact because every alternative is blocked by conservation laws and quantum selection rules. Energy is present, but unusable. It is tempting to imagine nuclear energy as something trapped, waiting to escape. But that image is misleading. The energy is not trying to go anywhere. It has no direction, no preference, no intent. It is simply part of the accounting required for the nucleus to exist in its current state. Only when the universe offers a legitimate alternative does the energy change form. This is also why nuclear reactions require such specific conditions. In fission, an incoming neutron provides exactly the right disturbance, opening a pathway that was previously closed. In fusion, extreme pressure and temperature bring nuclei close enough for new quantum states to become available. In radioactive decay, a subtle quantum allowance exists that permits a slow, probabilistic transition over long timescales. In every case, the release of nuclear energy is not caused by excess, but by permission. The rules change, or a new option becomes available, and the system responds immediately. Without permission, even infinite time would accomplish nothing. This rule-based stability is one of the deepest sources of calm in physics. It means the universe is not balanced on a knife edge. It means that vast energies can coexist with delicate structures without conflict. It means complexity is possible. Life is possible. Memory is possible. Matter does not constantly unravel because the rules do not allow it to. At a human level, this explains why nuclear energy feels both powerful and distant. It is not something we encounter accidentally. It does not leak into daily experience. It requires deliberate alignment with the deepest rules of matter. When we interact with it, we are not releasing something unstable. We are carefully opening a door that is otherwise sealed. This also places responsibility in a clearer light. Nuclear energy is not dangerous because it is chaotic. It is dangerous because it is precise. When conditions are met, the outcome is not gradual or forgiving. The rules permit release, and the release follows exactly. There is no friction to soften it, no inefficiency to dilute it. The same precision that keeps matter stable makes nuclear energy uncompromising when it appears. Yet even this severity has a kind of elegance. The universe does not hide energy behind mystery or randomness. It hides it behind consistency. The same principles that prevent nuclei from falling apart are the ones that allow us to predict, measure, and understand nuclear processes at all. There are no surprises, only consequences. Seen through this lens, nuclear energy is not a threat embedded in matter. It is a demonstration of trust. The universe trusts its own rules enough to allow immense energies to exist quietly, knowing they will remain contained unless every condition is satisfied. That trust is what gives the world its reliability. Matter does not fall apart because it does not need to. It has already found arrangements that satisfy the deepest constraints available. Nuclear energy is the record of how much adjustment was required to reach those arrangements, and how much could be released if even better ones become accessible. Most of the time, they do not, and so the energy remains where it is, supporting mass, enabling structure, and allowing the universe to be old, complex, and calm. In this way, nuclear energy is not an exception to stability. It is one of its strongest proofs. When we step back from all of this, what remains is not an explosion or a warning, but a picture of remarkable coherence. Nuclear energy turns out to be neither mysterious nor separate from the rest of physics. It is simply what matter looks like when it is held together by the strongest rules the universe has. At the smallest scales, nothing is loose or improvised. Protons and neutrons exist because quantum fields allow them to. Nuclei exist because forces balance with extraordinary precision. Mass exists because energy has already been spent to create stable arrangements. Nuclear energy is the record of that expenditure, written into the structure of matter itself. This is why nuclear energy does not behave like a fuel. It is not consumed, it is revealed. When a nucleus changes, what we witness is not energy being created, but energy being reassigned. A configuration that once required more energy gives way to one that requires less, and the difference appears in forms we can detect. Heat, motion, light, radiation. Familiar experiences arising from unfamiliar depths. Seen this way, nuclear energy is deeply conservative. Nothing is wasted, nothing is spontaneous. Every release is balanced by a more stable outcome. The universe does not trade stability for spectacle. It trades one stable arrangement for a better one, and accounts for every unit of energy along the way. There is something quietly reassuring in this. The same principles that allow stars to shine for billions of years are the ones that keep matter around us intact. The same quantum rules that permit nuclear reactions also prevent them from happening accidentally. Power and restraint are not opposites here. They are partners. Even the immense scale of nuclear energy begins to feel less overwhelming when understood in context. Its density does not come from excess, but from compression, short distances, strong forces, long times. Energy accumulated patiently, often since before planets existed, waiting not for an opportunity, but for permission. This patience is everywhere. It is in the nuclei that make up the Earth's interior, still releasing heat from ancient radioactive decay. It is in the atoms forged in long-dead stars, now quietly forming rocks, oceans, and living cells. It is in the matter of your own body, stable not because it is simple, but because it is deeply constrained. According to quantum physics, then, nuclear energy is made of relationships. It is made of how fields interact when space is limited. It is made of how forces balance when particles are forced close together. It is made of the universe's insistence on consistency across scales, from the smallest nucleus to the largest star. Nothing about this requires drama. Nothing about it demands fear. It asks only for careful attention. When we look closely, nuclear energy becomes not a disruption of nature, but one of its clearest expressions. It shows how much the universe values order, how much it invests in stability, and how rarely it allows that investment to change. In the end, nuclear energy is not hidden fire inside matter. It is the quiet cost of structure. It is what it takes for matter to exist at all, paid once and carried forward through time. Most of the time, that cost remains invisible, folded into mass, holding the world together without asking to be noticed. And when it does appear, it does so because the universe has allowed it. Not sooner, not later, exactly when the rules say it may. That is what nuclear energy is made of. Not violence or mystery, but patience, precision, and the deep calm of rules that have never been broken.